Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Bessel functions and how to numerically evaluate them. In the previous lecture, we saw that we can use this definite integral 1 over pi 0 to pi cosine of x sine of theta minus n theta d theta to calculate the Bessel function of the first kind when the parameter of the Bessel function is an integer. So this integral only applies when the parameter of the Bessel function is an integer. And we said that, okay, x is inside our integrand, the function that we are trying to integrate. So each time a new x is being passed in and being calculated, then we have to change our integral function. That's why in this method Jn that calculates based on the index and x, we are redefining or reassigning our integral function based on the new value of x. So our integral function is 1 over pi cosine of x sine of t minus nt, and t is the parameter of integration, and we call our integral object that does the integration and has all the numerical integration methods, and set the integral function to this new value, which is a functional interface. So we're using lambda expression, and then we call one of our methods. And we saw that Romberg and Simpson, or even Simpson, are overkill because we don't really need that much accuracy, and a center rectangle with an error of delta x squared will give us good accuracy anyways. And we said that even when we looked at the convergence of the center rectangle for different values of n and x, we saw that an order of for small values of x, maybe x between 0 and 100, we only need like 50, the order of 50. So we can just divide the interval for x into different regions, and based on those we can assign the order 50, 100 or something. But now what do we do if the parameter of the Bessel function is not an integer? So here I'm using alpha. We could also use nu. Some notations, some books use alpha, some books use nu, right? I'm going to use both of them, so you will get used to both of them. So here I'm using alpha, and alpha denotes a non-integer index, right? And what happens here is that we still end up with that part of the integration, which is from 0 to pi 1 over pi cosine of x sine of t minus alpha t dt. But then there's another term, and unfortunately the other term is an infinite integral, or as we call it, an improper integral. An improper integral is basically an integral which one of the bounds or both bounds are infinity. And the way we define it is just from 0 to infinity. We use the notation of 0 to some number a, and then we take the limit as a goes to infinity. If that limit exists, then we say that this improper integral exists. Okay? Now there is a leading term in this improper integral, which is sine of alpha pi over pi. And you immediately see that if alpha is an integer, sine of n pi for any integer, 0 plus minus 1 plus minus 2, etc., is always 0. That's why for integer alpha, when alpha is an n integer value, we don't see this other term. It's not because of the integer, it's because of this leading term, that is sine of n pi is always 0. All right? So what do we do here? So again, now we define jn or j nu or j alpha, right? I'm still using the notation of jn, but I'm overloading the method parameters. So in the previous slide, we had this method jn with int parameter and double x. I'm using a double alpha and double x, right? So the first parameter is overloaded. And what we're saying that obviously the first check is to make sure that alpha, even if this method is invoked, we have to make sure that alpha is not an integer actually. So if we use something like 2.0, 2.0, it's still an integer, right? Even if the format of the number is double. So what I'm saying is that if the absolute value, when I convert alpha to an int and take the difference from the actual value of the double value of alpha, if it's less than 10 to the negative 10, I mean, we could also, because the behavior of the Bessel function, this could be even maybe something like e to the negative 5. 10 to the negative 5. It means that this alpha is pretty much an integer. And then we just call our method that acts on an integer parameter. So I'm converting alpha to int and call that method, all right? So this is the first check. So even if this function is being called, if alpha is actually an integer or close enough to an integer, then we can just consider an integer, all right? And the reason that calculating the integer doesn't have this other function, other integral, so it's pretty easy to calculate that. Now what to do when alpha is actually a double number, it's not an integer? So we have to calculate two integrals. The first one, obviously, again, our func j. This time we also have another integral function, which is func jn inf. So func jn inf is basically calculating this infinity integral, this integral which has a bound. The upper bound of the integral is infinity. So func jn is like before. We have this 1 over pi cosine of x sine of t minus alpha t. And func j infinity is minus 1 over pi sine of alpha pi, all right, times the exponential of minus x sinh sine hyperbolic. This is a hyperbolic function t minus alpha t, all right? And then we have two integral, or we can use one integral object, integral jn. For first term, we set the integral function to func jn, which is this part, and then evaluate that integral, the first integral jn dot. Again, Romberg and Simpson is probably overkill. We can just use the center rectangle, that's fine, and we'll look at the convergence anyways. So Romberg and Simpson from 0 to pi with some order, some number of sub-intervals. And then when we calculate this, we take our integral object and set the integral function to this part, minus 1 over pi sine of alpha pi e to the minus x sinh of t minus alpha t. So we change the integral function and this time calculate it from 0 to some large number. So we cannot have infinity here. So this is basically some large number. And we have to decide what number to use, right? But in general, this is just some large number with some order. And then when we calculate them, we add them together, all right? That gives us a relatively good approximation of j alpha of x when alpha is not an integer. And here I'm plotting 4 Bessel functions, j 0.07, 1.95, 2.32, and 3.88, all right? So let's head to Eclipse and try to look at the convergence. All right, as before, we have this special func Java project, and we have Bessel function integration. And the default order is 300. And then this is the method we looked at previously, jn, with the parameters of int and double. And this is now the method we are looking at, jn, with the parameter of double, alpha and double x. And again, Java allows us to have the same declaration of the method with different parameters because of method overloading, right? So we are taking advantage of method overloading because the compiler is able to confer which method is being invoked at any given time based on the type of parameters, right? So the first check is the integer. We can say this is, let's say, 10 to the negative 5. And then we're calculating the first integral, second integral, and then add them together, all right? So we had this test class, test jn integration. We looked at the integer cases, and now we want to look at the non-integer cases. So I'm going to create a new method, public static void test3. In test3, what I'm going to do, basically, I'm going to copy the same thing here. Okay. I'm creating my Bessel function, and let's say j 0.5 or 0.7, for example. So here we're passing it j 0.7. Now it already knows that it has to invoke the double alpha, all right? So let's run this. All right, so we have an error because we need to change this one too. It takes quite some time. That's because we're using Romberg integration, but you see that it is able to calculate the Bessel function. So now let's go back to this Bessel function, and instead of Romberg on Simpson, I am going to just call the center rectangle. Center rectangle. All right. Similarly, for the second term, we probably don't need Romberg, so we just do center rectangle. And I'm calculating from 0 to 100. So the question is, what is the best number to put in here? And obviously that depends on, so if we go back, that depends on this function, right? Depends on the x value. And one important thing here is that what if x is negative? So if x is negative, then this integral diverges, all right? So basically what we need to say here is that this equation, j alpha of x, only works for x positive. So only for x positive. You have to be careful. This equation, this integral definition of Bessel function, we saw that the first term, if alpha is integer, then we don't have this second term, and this proper integral works for anything, positive x, 0x, and negative x, right? But if alpha is non-integer, then this integral definition works only for positive x. Now your first question would be, what happens if x is negative? Do we get infinity? And the answer is no, you will get something else. So I'm going to run Mathematica here and show you what Mathematica calculates, and we will look at this later when we implement it in Java. So in Mathematica, I can define Bessel J and give it, let's say, 0.7. Let's say first 0.1, right? And then minus 20. And let's ask for the numerical value. So we pass it to the n function, numerical value, and we calculate. It gives us a number, right? Minus 0.0668331, right? Now, instead of this, if I put 0.7, what do you expect to see? Let's see. Wow, we're getting a complex number, not a real number. So what happens here is that if x is negative, this integral becomes infinity. But that doesn't mean the j becomes infinity. What it means is that this definition or the representation of the Bessel function is not correct, is not valid for the negative x when alpha is a non-integer number, all right? So we have to use another definition. We will see that the power series, the definition based on power series, actually works. So when x is negative and alpha is non-integer, this definition doesn't work, all right? And the Bessel function actually becomes a complex number. And so let's go back here. So I'm going to test with the center rectangle for Bessel 0.7. And you see this is much faster, and we're still getting a relatively good result. And the next thing, again, just like the integer part, what I'm going to do, I'm going to create a sequence. And for that sequence, I'm going to look at the convergence for different orders. So public, static, void, test4. We want to see, so the default order, I just set it to 300 because it probably works for any number, a small or large value of x. So we have to go here and first we check for whether or not alpha is in fact an integer. So if it's not an integer, then we check whether or not x is negative, right? If x is negative, we're going to say that basically sysout results, okay, maybe jn of new and x results, or maybe is a complex number, so we cannot in fact return a double number, right? And then what we're going to say here is pass x as a complex number. By complex number I mean just set it as x, which is the real part, plus 0 times j, because we're going to implement something else for complex numbers. And then we're going to obviously return a nan value, double.nan. All right, so when alpha is non-integer, we cannot have negative x. And again, back to Mathematica, if I set this to positive, Bessel function is a real number. If I set it to negative, even a small number like -2, Bessel function is a complex number. So for non-integer index 1.2, Bessel function is a complex number for negative x values. All right, and to reiterate, that's because this integral representation is only valid for x positive. For negative x, this definition is not valid. We have to use another definition for Bessel functions. And all right, so we put an else statement here and put all these stuff in the x. All right, and again, double check our test value works. The speed of calculation is relatively good, 169. We definitely do not need higher, more accurate integration like Simpson or Romberg. But then in test 4, let's also look at the convergence. So I'm going to calculate j, let's say 0.7, and at some number 20. What did we calculate here? Okay, let's calculate 0.7 at 20. It should be 0.133144. So let's see. Sysout Bessel jn double 0.7 and 20. All right, so we're going to sys it out. Let's print it to the terminal or to the console, and then create a sequence. Calculates j.7 at 20 at x equals 20. So this is a non-integer index, and then we're just increasing the order of integration. All right, so set integration order, and we are assuming that we're using the same order for both of these. All right, and then plotting the result. So the first thing here is that the value of Bessel 0.7 at 20. Let's go back to mathematics. We're getting 14. We're getting this number, and let's see. We are getting 14, 28, 96. Mathematica is returning 133, 144. So our calculation is not that accurate. And again, the main culprit is the second integral, which is the improper integral. So as you can see, we do get a convergence. The convergence is definitely not good. So after one, first of all, as you can see, we are calculating at 300, right? Which returns 0.143. And we see that we still do get a better number if we go to 1000. Which is 135, and it's closer to 133 that Mathematica was returning. So the problem is that our integration is not fast enough. So instead of this center, we can go I believe the center rectangle was good, so the main problem is probably from here. So what we can do, maybe go to 1E3. Let's see if this helps. 1455. So no, it doesn't help. So for this part, I'm going to call the Simpson method. Let's see if that can help. Simpson. We're getting 1294, so here. So we pretty much need a much better accuracy for the order of integration. So let's do this. Let's go back to center rectangle. Here we put 1000. All right, now we're getting pretty close. 1355, 1351, and yeah, as you can see, with 1000 we're getting close. And let's make this 2000. We're getting 1337. Yeah, it's almost converging, right? Now what happens, instead of calculating this, I accelerate it with a Richardson. 1337. And we see that the convergence is relatively good. Basically, at 100, we are at 1335, and it goes up. If I don't do the Richardson, we see the convergence is not bad. So if I go instead of 1000 to 2000, let's see what happens. It takes some time, but we are almost getting there. 13.1336.8. How much is the value? 0.133144. So we still have some error, but that error mainly comes from here. So if we increase this and go to 2000, and let's also keep 1000 here, 1448. So the problem here is that increasing that interval here is seems to be causing some stability issue. Let's set this to 50. 1333. So I guess this is a relatively good number. So let's go back to here, test 3. In test 3, we are plotting from 0 to 50, 0.7, and now let's time it. So what we're doing here is we are setting the order to 300, and then we're using the center rectangle. Let's see how long it takes. 800 milliseconds. It is still good, and at 20 we are getting how much? 13, something about 1335, and Mathematica is returning 1331. So we're close enough, okay? All right, so we can also test for other cases. Instead of having a 0.7, let's go to a large value like 5.7. And here we see that we get another Bessel function. Bessel 5.7. And typically, again, using integration is not the way that we actually calculate Bessel functions for small values or large values, and we will look into the other ways instead of integration to calculate the Bessel functions. All right, I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.